Welcome to the deep dive. Today, we are putting on the highly specialized visor of a global automotive engineering strategy consultant and a senior powertrain architect.
That's right.
The world we're stepping into is Formula Student Electric, or FSE. This is where engineering students are pushing the very limits of electric vehicle design, but under, almost impossible time and budget constraints.
Oh, absolutely. This isn't some theoretical exercise.
No, this is high-stakes, real-world application.
And the stakes are, well, they're tremendous. When we analyze the global Formula Student data, the numbers are just brutal.
Right.
Our sources confirm it. Historically, over half of all electric race cars, especially the ones built by new university teams, they just retire prematurely.
So they don't even finish the main event.
Many don't even start. They either fail the electrical scrutineering before the flag even drops, or they suffer a catastrophic thermal management breakdown during that grueling 22-kilometer endurance event.
That failure rate is exactly why we're doing this deep dive. It's crucial. We're unpacking a very specific, almost non-negotiable blueprint, an electric drive system, or EDS engineering requirement specification, a detailed SOR.
Right, a statement of requirements.
And this document is designed to sort of short-circuit those typical first-year mistakes and guide a new team in building a world-class, competitive, and this is the key reliable electric racing car.
The primary mission is survival. And in engineering terms, that translates directly to system optimization and reliability. We are working under the hard ceiling of the FIA 80 kilowatt power limit.
Okay.
So the SOR we put together, it moves way beyond just, bolting a few components together. It defines what we're calling EDS 4.0. This is the mature phase of FSE development.
We've heard about earlier phases before. What exactly defines this jump to EDS 4.0?
Well, EDS 1.0 was often, is literally just strapping a golf cart motor onto an old combustion chassis.
Right.
EDS 2.0 moved into proper component integration. Just a recognized motor, but a proper inverter.
And 3.0?
EDS 3.0 was this phase of trying to copy the top European teams, just blindly. And that often resulted in these overly complex, completely unreliable systems that the teams didn't understand.
So what makes 4.0 different?
EDS 4.0 is defined by two strategic pillars. First, data-driven decision-making. Second, total efficiency optimization.
So it's a shift away from just intuition.
It's a total shift from intuition to simulation. We have to model dynamic thermal loads. We have to conduct rigorous verification and validation, the whole DVP&R approach, and ensure every single component works flawlessly with every other component.
I see.
Our architecture, our thermal systems, our control logic, it all has to be integrated from day one to deliver reliability. Because for a new team, reliability is the only true competitive advantage.
That makes perfect strategic sense. I mean, you can't win if you don't finish.
Exactly.
Okay, let's unpack this then. The first, and I imagine the most critical strategic decision that sets the tone for the entire build, and it sounds like where most new teams falter from overambition, is the architecture.
It is.
Are we chasing the cutting edge, or are we chasing the finish line?
That brings us squarely to requirement 4.1, the 80 kilowatt architecture showdown.
So the technical constraint is that hard limit. The total power you can draw from the accumulator, which is regulated by the VCU, it cannot exceed 80 kilowatts. That's what, about 107 horsepower total?
And this is the source of the big strategic engineering paradox for new teams. It doesn't matter if you manage to install 4 separate motors, each rated for, say, 35 kilowatts as a peak power.
Giving you 140 kilowatts of potential power on paper.
Right, but you still have to throttle that cumulative output all the way down to 80 kilowatts. And this fundamentally changes the entire cost-benefit analysis of adding complexity.
Okay, wait, I have to challenge this strategic mandate right away. If the top teams, the ones winning everything, AMZ, TU Delft, if they're all running four-wheel drive, aren't we condemning this new team to, mid-pack results by mandating a simpler solution?
I was waiting for that question.
Why risk performance just for reliability?
And that is the quintessential strategic risk assessment that defines the success or failure of a new team. We have to analyze architecture A, that 4WD in-wheel motor setup, through the lens of a new team's resources and their timeline, not through the lens of a 5-year established multi-million-dollar program.
Fair enough. So let's break down architecture A first. What is the undeniable performance edge that makes all the top teams pursue it?
It boils down entirely to one concept: yaw moment control via torque vectoring.tv.
Okay.
So imagine you're entering a tight corner. A traditional differential, it just transfers torque. A 4WD system with in-wheel motors can independently modulate the slip ratio on all four wheels at the same time. It can apply aggressive positive torque to the outer rear wheel while simultaneously applying negative torque.
Do regenerative braking.
Exactly, through regen to the inner front wheel.
So the drive system is actively turning the car in addition to the steering rack.
Precisely. You're creating an additional powerful turning force, a yaw moment, which significantly improves your corner entry and your corner exit speed.
And the data backs this up.
The performance metrics are compelling. Simulations show that a mature 4WD TV system can cut skid pad times, that's the tight figure-8 test that demands immense agility, by a significant 1.3 to 1.36%.
Which, in a competition measured in hundredths of a second, is a massive gain.
It's an eternity.
And then there's the energy management benefit on top of that.
Yes, which is critical for the endurance event. Because you have drive motors on all four wheels, you can maximize your regenerative braking across both the front and the rear axles.
So you're recovering more energy.
Much more. And that energy recovery efficiency means you need less initial energy storage to begin with. Our analyses show that a maximized 4WD regen setup could potentially allow a team to shrink their entire high-voltage battery pack by 15 to 20%.
Which is a direct and significant mass saving.
And that compounds the performance advantage.
So the performance case is, well, it's overwhelmingly strong. Now let's bring it back to that cold, hard engineering reality for a new team. Why is this a trap?
Because the complexity of 4WD is nonlinear. It's not just twice as hard as 2WD. It introduces layers of engineering difficulty that multiply the required man-hours and expertise.
Okay, start with the dynamics. The unsprung mass penalty.
This is the physical killer. In-wheel motors and their planetary reduction gearboxes, plus the cooling circuits, the high-voltage cables, all of that is mounted outside the chassis structure. It's all classified as unsprung mass.
And how much weight are we talking about?
In our analysis, this setup can add 5 to 7 kilograms of weight per corner compared to an inboard system.
And what does that increased unsprung mass actually do to the car dynamically?
It brutally degrades your mechanical grip. When the car hits a track imperfection, a little bump or a curb, that heavy unsprung mass resists movement. It forces the suspension to work harder, and crucially, it causes the tire to momentarily lose or dramatically vary its contact patch pressure with the asphalt.
So if the tire isn't loaded correctly?
Your ability to transmit lateral forces, to corner, just drops off a cliff. You can have the best TV software in the world, but if the tire isn't actually gripping the road, it is completely useless.
And mitigating that penalty means diving into some extremely advanced suspension damping expertise.
Exactly. You'd need to master complex, highly tuned, maybe even active damping systems just to recover the mechanical grip you lost by choosing the in-wheel motors in the first place. That requires years of vehicle dynamics iteration and professional-grade simulation tools that are just far beyond the scope of a typical first-year team.
And beyond the dynamics, the sheer manufacturing hurdle of this architecture seems daunting.
Packaging is the enemy. You have to fit a powerful motor, usually a proprietary planetary gearbox, and the necessary cooling jacket, all inside a compact 10-inch wheel rim.
That's incredibly tight.
It demands high-precision CNC for the internal components, and the lack of space severely restricts your cooling surface area. So you've now compounded your thermal challenge, which we already know is the single biggest risk factor for any team.
And then we get to the Achilles heel you mentioned, the control algorithm.
This is where it all falls apart for new teams. All those potential performance benefits, that 1.3% lap time cut, are 100% dependent on the sophistication and maturity of the torque vectoring control software.
And that's not something you can just buy off the shelf.
Not at all. Our sources confirm that achieving a mature, reliable, and predictable TV algorithm requires a dedicated 2 to 3 year iteration cycle. That's simulation, hardware-in-the-loop testing, driver feedback, rinse and repeat.
And if the algorithm is bad?
If it's poorly executed or unreliable, the system can suddenly apply unwanted yaw moments. This makes the car unstable, unpredictable, and frankly, harder to drive aggressively than a simple traditional rear-drive car. It becomes a safety issue and just an operational nightmare.
That strategic defense it's compelling. The high-risk, high-reward approach of 4WD is a resource sink a new team simply cannot afford.
Which is why the SOR mandates the pivot to Architecture B.
The strategic reliability of 2WD rear inboard.
This is the completion-first strategy defined in the SOR. It uses a mature, proven, and mechanically much simpler setup.
Can you describe the key elements of this architecture for us?
Sure. We use two high-power density motors. You can think of liquid-cooled units like the MRAX 228 or a Fisher TI Euro 85, and we mount them securely inside the chassis structure.
So the mass is sprung.
The mass is sprung, and these motors drive the rear wheels through half shafts, usually via a simple gearbox or a chain drive.
What are the primary performance and efficiency gains here that, compensate for not having 4WD?
Well, first is efficiency. By selecting two motors with continuous power ratings between 40 and 50 kilowatts, we perfectly match that 80 kilowatt hard limit. This lets the motors operate much closer to their peak efficiency zones, which are typically 95% or higher.
As opposed to running 4 motors throttled way back.
Right, running 4 motors constantly throttled back at 20 kilowatts each, where their efficiency often dips significantly. And secondly, we still retain electronic differential functionality on the rear axle.
So you still get some cornering assistance.
You do. It uses subtle torque biasing between the left and right rear motors to enhance cornering and dramatically improve traction management out of a bend. It's not full yaw moment control,
Right.
but it's a very robust, proven substitute.
And the physical engineering gains?
They're immediate, and they're critical for reliability. You save roughly 15 to 25 kilograms of overall mass compared to a 4WD setup, and all remaining mass is sprung, which dramatically improves suspension response and tire fidelity over that critical endurance track surface.
And it's simpler.
Much simpler. You have a simplified mechanical design, no complex in-wheel planetary gears, and you reduce the complexity of the high-voltage wiring, which minimizes the risk of EMI, electromagnetic interference, that can corrupt your VCU or CAN communication.
So we arrive at the mandatory strategic requirement.
Yes. SOR 4.1 REQ-01. It explicitly mandates the 2WD rear independent drive inboard architecture for the first 2 build cycles. This ensures the team focuses its resources on passing scrutineering and completing endurance, which is how you build institutional knowledge.
Okay, let's nail down the specific motor selection next.
So, SOR 4.1 REQ-02 specifies the motors. We require 2 units rated for 40 kilowatts to 50 kilowatt as continuous power.
And the emphasis is on continuous, not peak.
The emphasis is on thermal headroom. While 80 kilowatt is the peak, we are designing for that 22-kilometer endurance event where sustained high power is needed. By using motors whose continuous rating exceeds the required continuous power for the race, we ensure the system can maintain that 80 kilowatt peak safely without entering thermal derating.
So you're not pushing the motor to its absolute limit for long periods.
Exactly. If you try to push a 30 kilowatt continuous motor to 40 kilowatts for too long, it's going to overheat and derate. This setup prevents that.
And what about the transmission choice? SRR 4.1 REQ-03. You're recommending both a racing chain and helical gears, but with a non-negotiable safety factor.
The safety factor has to be greater than 1.5. This is fundamental. Electric motors deliver their maximum torque virtually instantaneously from 0 RPM. This creates a massive sharp torque shock that can just shatter poorly specified gear teeth or shear keyways.
So it has to be over-engineered.
Massively over-engineered to handle that instantaneous shock. The 520 racing chain is highly recommended for a new team because, while it might be slightly less efficient than gears, it offers incredible fault tolerance. It'll often stretch or wear before it catastrophically fails.
And it's easier to work with.
And it allows for incredibly easy gear ratio changes during initial testing, which is vital for tuning your acceleration and top speed before you ever get to the competition.
Okay, so we've specified the architecture and the hardware, but the reliability Achilles heel, it remains. Heat. If the RMS current is the unseen enemy, how do we physically stop it? That moves us squarely into the most critical section of this entire SOR.
It does.
This section represents the difference between a car that runs for 10 minutes and a car that actually completes the 22-kilometer endurance event.
Without a doubt. Thermal management is the single biggest factor in FSE completion statistics. The crucial insight, and it's one that new teams consistently miss, is that you have to design your cooling systems for RMS root mean square heat load, not just for the peak 80 kilowatt power.
Why is RMS or IRMS the correct measure? Can you break down the physics for us there?
Sure. So, heat generation in your electrical components. Motors, inverters, cables. It's governed primarily by Joule losses, which are proportional to the square of the current. P loss is proportional to I squared.
Right.
The racetrack involves constant hard acceleration and hard braking. So while your average power draw over a lap might be a modest, say, 20 kilowatts, meaning a relatively low average current, the moments of peak acceleration draw massive, short bursts of current, maybe 150, 200 amps in a 600-volt system.
And because heat is proportional to I squared,
Those peak current spikes contribute disproportionately to the overall heat accumulation in the system.
So IRMS smooths out those peaks but gives them the proper weighting in the calculation.
Exactly. IRMS is calculated by squaring the instantaneous current over the entire lab, averaging that squared value, and then taking the square root. So if your average current is, say, 30 amps, the IRMS might be 80 to 100 amps. And that IRMS value is the current we must design our components to handle continuously because it represents the actual sustained heating load.
Which is why SRR 4.2 RUQ01 mandates modeling that IRMS from track data.
You have to get it right from the start.
And we also have to model for those unique moments of high-risk failure, particularly that 3-minute static driver change period during the endurance event. That just sounds like a recipe for thermal disaster.
It is a critical point of failure. We call it heat soak. During the first 11-kilometer segment, your motors and inverters accumulate a massive amount of heat internally. When the car is parked for those 3 minutes, your dynamic airflow stops. The fans and pumps might be shut down or run at a minimum speed to conserve the low-voltage battery. So the thermal energy that's trapped inside the motor windings in the inverter junction layers, it just spreads out. It soaks into the housing, the mounting bolts, the static casings.
And the moment the car restarts, the newly energized components immediately begin generating heat on top of that already elevated baseline temperature.
And that spike is often enough to instantly exceed the thermal limits of the sensors or the IGBTs, which triggers an immediate hard power derating by the VCU.
So the driver is suddenly left with, what, 20 kilowatt of power instead of 80?
Exactly. The car becomes slow, uncompetitive, and potentially unable to even complete the remaining 11 kilometers.
This necessitates the rigorous mathematical approach you've defined in the SOR, the lumped parameter thermal network, or LPTN modeling. I think the audience needs to understand not just that we need one, but how it fundamentally works.
The LPTN is essential for predicting temperature rise in real time. It models the entire thermal system like it's an electrical circuit. We define key thermal nodes, like the stator windings, the rotor core, the inverter junction layer, the housing, the coolant inlet and outlet.
Okay.
And these nodes are linked by thermal resistance, RF, which is analogous to electrical resistance. It represents how difficult it is for heat to flow between nodes. They also have thermal capacity, CDIF, which is like electrical capacitance. It represents how much heat they can store.
So by knowing the heat input RP loss and tracing its path through these resistances and capacities, we can predict the temperature at every critical internal point in the system.
Exactly. And this is vital for understanding motor losses. The primary heat source is the motor, generating between 4 and 6.4 kilowatts of heat at peak 80 kilowatt output. We break this down into two types of losses.
Copper loss and iron loss. And copper loss is where that dangerous positive feedback loop starts, isn't it?
It is the runaway train. Copper loss, or PQ, is the resistive loss. PQ equals I squared RS, where RS is the winding resistance.
Okay.
The problem is that the resistivity of copper increases significantly with temperature about 0.4% per degree Celsius. So as the motor heats up, RS goes up, which increases PQ, which generates more heat, which raises RS even further.
Yow.
The LPTN model has to dynamically account for this positive feedback loop, or your temperature prediction will be wildly optimistic and completely wrong.
And the second component, iron loss.
Iron loss, or PFE, comes from hysteresis and eddy currents in the stator core. This loss component is heavily dependent on switching frequency and magnetic flux density, which means it generally becomes dominant at high RPM.
So like flying down a long straight.
Exactly. If your motor selection has poor core material, you can see significant thermal spikes in the high-speed sections of the track.
Okay, next, let's look at the inverter losses. Even at 97% efficiency, 2 to 2.5 kilowatts of heat is significant when we're talking about components with very low thermal mass.
And this is where thermal sensitivity is highest. The power modules, the IGBTs or SiC MOSFETs, are tiny semiconductor packages. They have extremely low thermal capacity, CQOTC, which means they absorb very little heat before their temperature skyrockets. Their survival depends entirely on the flow and temperature of the coolant.
And this is where we connect the thermal model directly to component safety.
Absolutely. For a typical FSE inverter, like the Cascadia CM200DS we often recommend, the semiconductor junction temperature must be maintained below 80 degrees Celsius. That's to ensure long-term reliability and to prevent immediate critical failure.
And to achieve that
internal junction safety, the coolant inlet temperature cannot exceed 60 degrees Celsius. If that inlet temp creeps up to 65 or 70 degrees, the VCU will immediately initiate a hard power derating. It'll slash the power output to protect the investment.
And finally, the accumulator. The heat load is smaller, maybe 500 watts to 1.5 kilowatts, but the safe operating window for lithium cells is the narrowest of all.
The chemical stability window is incredibly tight, typically 20 to 55 degrees Celsius. If they run too cold, you lose capacity. If they run too hot, you risk catastrophic failure, and you severely degrade the lifetime of the entire pack.
And it's hard to get the heat out.
It's very tricky. The path for heat rejection inside a dense battery enclosure, even with cold plates, often presents a really high thermal resistance. So the LPTN model has to track the hottest single cell, because that one cell dictates the performance limit of the entire system.
So summing up all these calculated losses, motors, inverters, cables, we arrive at the total cooling requirement, SOR 4.2 REQ02.
Yes. Based on that IRMS modeling and the component loss summation, the liquid cooling system must be designed to continuously dissipate a massive, sustained 10 to 12 kilowatts of heat from the dual motors and dual inverters.
And that's under race conditions.
And this capacity must be validated at a 35 degrees Celsius ambient temperature to simulate the worst-case hot European or U.S. summer race days.
And if we can meet that 10 to 12 kilowatt rejection target, what are our internal component thresholds?
The acceptance criteria are strict. We have to keep the motor windings below 100 degrees Celsius and that temperature-sensitive inverter junction below 80 degrees Celsius. Anything above that means a failure of the thermal design, regardless of how fast the car is otherwise.
We know we need to reject 10 to 12 kilowatts of heat. So now we move from modeling the problem to physically solving it. Our sources highlight a really common mistake. New teams prioritize size over function when they're selecting a radiator. They just think bigger is always better.
That is a classic misapplication of intuition. The solution is matching the radiator's design to the system requirements and focusing on two key metrics: flow resistance, delta P, and effectiveness, epsilon.
And you recommend an aluminum structure.
Yes, aluminum is superior for lightweighting and for surviving the severe vibration of track use, specifically a dual-pass or cross-flow structure.
What's the advantage of the dual-pass design for the listener who isn't a fluid dynamics specialist?
So in a simple single-pass radiator, the coolant enters one side and exits the other. A dual-pass structure forces the coolant to travel through half the core, loop back, and then travel through the remaining half.
So it's in there for longer.
It essentially doubles the contact time between the hot fluid and the core surface, which dramatically increases the opportunity for heat transfer. We're aiming for a high effectiveness, an epsilon, between 0.4 and 0.6. This just maximizes heat rejection for a given radiator size.
And you mentioned a brilliant strategic shortcut for new teams regarding the sizing.
Yes, the strategic beauty of matching components. We know we need 10 to 12 kilowatts of rejection. So a great engineering shortcut is recognizing that a single, high-quality, off-the-shelf motocross radiator, say one designed for a 450cc KTM or Honda, is already factory calibrated to reject roughly 10 to 12 kilowatts of heat from an internal combustion engine's cooling system.
That's a massive resource advantage.
It is. The strategic beauty is twofold. One, it perfectly matches the required thermal load we've calculated. And two, it's a COTS part commercial off the shelf with documented, validated performance. That saves a new team thousands of hours of CFD work and bench validation.
And for teams with a higher budget.
Specialized racing cores, like the C-Trad 6 series, are excellent alternatives because they offer documented low internal flow resistance, which helps simplify the pump matching process later on.
But, as we've established, even the best radiator is useless if air doesn't flow through it.
Right.
The low average speeds of FSE, mean ram air, is insufficient, which makes the fan strategy critical. That's SOR 4.3-REQ02.
Correct. And the fan must be chosen for high static pressure, not just maximum airflow or CFM.
Why is that?
When air hits the densely packed fins of the radiator core, it encounters a massive pressure drop, a flow resistance that's typically measured between 100 and 200 pascals. A cheap or low-performance fan, one that's designed for max CFM and open air, will have its flow rate drop to basically zero when it's pushing against that pressure barrier.
So we need fans that are purpose-built to overcome that resistance.
Precisely. We recommend high-performance curved blade fans, like the SPL 12-inch or 9-inch models. These fans are engineered to generate high static pressure, which is the force required to push the desired CFM through the core's flow resistance.
And they have to be robust.
They must be IP68 rated for water and dust immunity and controlled via PWM, pulse width modulation from the VCU, to modulate their speed based on temperature input. That saves precious low-voltage battery power during low-load periods.
Next up, the absolute performance differentiator, aerodynamic ducting. The sources say that without a sealed system, radiator efficiency can plummet below 50%. This is the forgotten performance element.
It is where good engineering meets good aerodynamics. Air is always lazy. It will bypass the radiator core through any available gap. The ducting has to force 100% of the air mass flow through the fins.
And the most critical component is the inlet diffuser.
Yes, the duct leading from the car's exterior to the radiator face.
And why must this duct expand or diverge?
This is a direct application of Bernoulli's principle. The air entering the inlet is moving fast, so it has high dynamic pressure. As the duct expands and slows the air down, it converts that high dynamic pressure into high static pressure.
I see.
It's this increased static pressure, the force per unit area, that acts like a piston, pushing the air mass through the flow resistance of the dense radiator core, maximizing your cooling effectiveness.
Is there an empirical design sweet spot for how much it should expand?
Yes, the source material points to a critical empirical ratio. The inlet area should be approximately 30 to 40% of the radiator face area. This compression and expansion ratio ensures you get the necessary static pressure rise while maintaining adequate mass flow.
And it has to be sealed.
Critically, the duct must be 100% airtight. We often use dense rubber or foam seals between the ductwork and the radiator core mounting surface. Any air that leaks around the edges is just lost efficiency.
And once the air is hot, where should we dump it? The outlet strategy.
You have to maximize the overall pressure differential across the core. The inlet provides the high static pressure, and the outlet has to be placed in an aerodynamically determined low-pressure region of the car,
Like over the diffuser.
typically over the rear diffuser or into the wake behind the side pod. This maximizes the sucking effect on the backside of the radiator, drawing the air through the system and minimizing the parasitic aerodynamic drag from extracting that hot air.
Finally, let's talk fluid dynamics within the cooling circuit. Given our 2WBD architecture, what is the optimal layout?
The recommended layout is a dual side pod approach. Ideally, the SOR pushes for separate cooling circuits, a dual loop system.
Okay.
One loop handles the motors, which can tolerate higher temperatures, maybe 70 to 90 degrees Celsius. The second, separate loop, handles the intensely temperature-sensitive inverters, ensuring they always receive the coldest possible fluid, ideally below 55 Celsius at the inlet.
But if space or budget forces a single loop, which I imagine is often the case for new teams, what is the mandatory fluid flow order?
The flow order is non-negotiable, and it's dictated by component sensitivity. Pump, then inverter, then motor, then radiator, and back to the pump.
So the inverter gets the coldest fluid first.
It must receive the coldest fluid from the radiator first because its protection limits are the strictest. The motors can handle slightly warmer fluid before the entire flow returns to the radiator for heat rejection.
And the final piece of this puzzle, matching the pump.
This is so often overlooked. You have to use an electric water pump, an EWP like the Davies-Craig AWP 115, but you must ensure the pump's flow pressure, or PQ, curve perfectly matches the total system flow resistance of all your components, hoses, and the radiator.
Because if it doesn't,
if the pump can't overcome the aggregate flow resistance, your flow rate and LPM will drop, resulting in insufficient heat transfer and ultimately system failure, even if the radiator itself is sized correctly. The whole system is only as good as its weakest flow link.
we've designed a strategy, we've selected the architecture, and we have modeled the thermal solution. But in professional engineering, a design is only a hypothesis until it's actually proven.
That's right.
This brings us to the formal methodology required by the SOR, the V-model approach, summarized in the Design Verification Plan and Report, or DVP&R. This is how we prove the EDS 4.0 system delivers on its promise of reliability.
The V-model is the backbone of mature automotive development. It structures the testing process into 3 sequential phases, moving from component testing in the lab all the way to full track simulation.
Okay, let's start at the base of the V. Phase I, component and bench testing. What happens before a single high-voltage cable is even run in the chassis?
So SRR 5.1 REQ01 covers inverter commissioning. This is foundational communication and safety testing. First, you verify the integrity of the CAN bus, the central nervous system of the car.
You need proof it's working.
You need proof that the heartbeat signal between the VCU, the BMS, and the inverter is stable, resilient to EMI, and functioning at the correct baud rate. Second is precise sensor calibration, particularly the motor encoder offset angle, which is required to ensure smooth and efficient motor commutation.
And what's the most critical test for reliability here, the protection logic?
Yes, we have to intentionally simulate catastrophic failures. We introduce simulated overcurrent faults, over voltage events, over temperature flags, to verify that the inverter's internal protection logic immediately cuts output within the prescribed, often sub-millisecond time frame.
So you're trying to break it on the bench.
You are.
Yeah.
If your failure detection is too slow or too unreliable, a fault that should just trip a warning light could result in a busbar short circuit or a completely fried power module. Proving this logic works is absolutely non-negotiable before dynamic operation.
And at the same time, we have to verify the thermal hypothesis from Section 2 on the bench?
Yes, SR 5.1 REQ-02 requires cooling system characterization. This is empirical verification. You build a standalone test bench using heating rods or dummy loads placed inside component simulators to replicate that calculated 10 to 12 kilowatts of heat generation.
And what are we specifically measuring?
We are measuring the actual heat rejection curve. By calculating the temperature difference, the delta T, across the radiator at various measured flow rates and fan speeds, we verify empirically that the system can indeed dissipate 10 kilowatts or more at our target 35-degree ambient temperature.
So we don't just trust the manufacturer's data sheet.
We never just trust the data sheet. We validate the system performance as it's actually built.
Okay, moving up the V now to Phase 2. Vehicle functional testing, focusing on safety compliance. This moves beyond the lab and tests how components interact in the real car.
Safety is paramount. SR 5.2 REQ-01 references the critical FSGIN.9 rule, which requires mandatory rain testing on the tractive system active vehicle. We have to verify that the electrical encapsulation, the sealing of all high-voltage components, holds up to water intrusion,
And that the safety systems work.
and that the insulation monitoring device, the IMD, activates correctly. If water breaches the system and the insulation resistance drops below the threshold, the IMD must flag it immediately. Failure here means instant disqualification at the competition.
The other key functional test is braking synergy, testing that complex interaction between mechanical brakes and regenerative braking.
This is essential for both safety and performance. SRR 5.2 REQ-02 requires rigorous testing of the brake system plausibility device, the BSPD.
Can you give a simple explanation of the BSPD for the audience?
Sure, it's a mandatory safety mechanism. The rule is simple and absolute. If the driver is applying the brake, say pressure detected above 20 bar, and is simultaneously requesting throttle or power above a tiny threshold, like 5 kilowatt, the VCU must instantly and completely cut all motor driving torque
And why is this required?
to prevent the car from pushing. If the motor is still generating driving torque while the driver is braking hard, it leads to severe control risk and potential component failure.
So the test validates the whole chain.
It validates that the sensor suite, which requires redundant brake pressure and position sensors, is robust, and that the VCU's cutoff logic is instantaneous and reliable. The VCU has to seamlessly blend regen with friction braking under normal operation, but the moment that safety threshold is breached, the motor torque is cut entirely.
We've reached the apex of the V. Phase 3, track endurance simulation. This is the final stress test where the whole design proves its worth.
This is it. SOR 5.3-REQ-01 defines this. The test protocol involves running the car continuously for the full 22-kilometer distance, but typically you're escalating the power levels.
So?
You'd run the first few laps at 70% of 80 kilowatts, then 85%, and finally full 100% bursts to really push the thermal limits to the point of failure.
And what's the mandatory data requirement during the simulation?
The data acquisition system, the DAQ, must be logging in real time every critical temperature. Motor windings, inverter IGBT junction temps, all the coolant inlet and outlet points, and the temperature of the hottest single battery cell.
And the RMS current.
Crucially, the IRMS must be logged continuously and correlated with the thermal accumulation. If your thermal model predicted 85 degrees at the windings after 22 kilometers, and the DAQ logs 105, your model is flawed and the thermal design fails.
And what are the acceptance criteria for this grueling test?
After completing the 22-kilometer run in simulated high ambient temps, we set the bar at 30 degrees C minimum. All critical components must still maintain at least a 10 degrees Celsius thermal safety margin below their specified maximum operating temperature.
And that 10-degree buffer is your insurance policy.
It's insurance against track variation, sensor errors, and ambient temperature spikes on race day.
And finally, the ultimate reliability check, the heat soak check. SOR 5.3 REQ-02. It sounds like we are deliberately trying to fail the car here.
We are. Immediately after the full 22-kilometer high-power run, the car has to be parked, and all active cooling pumps and fans shut down for 3 minutes, simulating that driver change.
And the DAU keeps running.
The DAQ continues to log temperatures. We have to verify that the temperature creep due to thermal inertia doesn't cause any component to exceed its maximum limit. If the core heat spreads and spikes an internal sensor or cooks an IGBT while the system is passively soaking, the design is fundamentally flawed and it requires a larger cooling reservoir or better component insulation.
The section concludes with the mandatory failure mode and effects analysis, the FMEA. This isn't just a document, is it? It's a proactive risk mitigation tool.
Exactly. The FMEA ensures we have a tested mitigation strategy for every high-risk failure mode. Let's take two specific high-risk examples. First, catastrophic cooling line bursts.
Okay.
The mitigation requires using raceback, often braided hose, and excluding pressure monitoring in the cooling circuit.
Yeah.
If pressure drops below a threshold, the VCU has to trigger a safe power data reading sequence.
And second, CAN communication loss, which sounds terrifying because the car loses all central coordination.
That requires redundancy. The mitigation often involves running redundant CAN buses for critical communications. In some high-power density applications, we even recommend optical fiber links instead of copper wire to completely shield those critical communication lines from the immense high-frequency EMI generated by the inverters and motor cables.
And the highest risk electrical failure, a potential IGBT breakdown.
This requires a robust layering of protection: thermal limits, overcurrent detection, and crucially, active discharge circuits. These circuits are designed to quickly and safely dissipate the massive residual charge stored in the DC bus capacitors upon system shutdown or a fault detection, preventing that lingering high voltage that could trigger catastrophic short circuits or arc faults inside the inverter housing. The FMEA process ensures that for every single risk, the mitigation is documented, tested, and implemented.
This deep dive has shown that architecting a competitive Formula Student electric powertrain is less about choosing expensive components and far more about mastering systems integration, reliability modeling, and rigorous verification. We've really seen the world through the eyes of a strategic engineering consultant.
We have, and we've defined the 3 strategic pillars for this new team's success. First, 2WD is the essential starting gate. It's the shortest, safest path to passing scrutineering and completing the endurance event by deliberately avoiding that nonlinear complexity and the crippling unsprung mass penalties inherent in 4WD in-wheel architectures.
Okay, pillar 2. Thermal management is the performance assurance policy. You can't rely on intuition or peak power figures. The IRMS heat load calculations have to drive all your design decisions.
That's right. You must design for the empirical necessity of continuously dissipating 10 to 12 kilowatts of heat, and that necessitates high static pressure fans and aerodynamically optimized fully sealed ducting.
And third,
Data models must drive all decisions. The LPTN thermal model, the track simulation for IRMS, and that rigorous 3-phase DDP&R plan must validate every single component selection, from the motor to the transmission ratio. This is the defining feature of EDS 4.0, moving past simple component assembly into true data-driven systems engineering.
So what does this all mean strategically? We've mandated the reliable 2WD system for the first year, focusing the team's limited resources on the achievable goal of completion. But the source material is explicitly clear. 4WD, with its extreme yaw moment control and highly efficient front and rear energy recovery, provides traction and energy management benefits that are just unattainable by rear-wheel drive.
It does.
It is ultimately the only path to world-leading championship status.
And that presents the ultimate strategic challenge. If 2WD rear inboard is the fastest way for this new team to finish their first season, and 4WD in-wheel is the key to winning their third or fourth,
then the real question for the strategic architect is,
when and how should they start diverting precious year-one resources now to developing the complex software, the control algorithms, and the suspension tuning expertise that will ultimately define their competitive 4WD future?
wow.
That dual-track challenge, focusing on today's survival while investing in tomorrow's dominance, is the strategic tension that lies ahead.
A truly fascinating engineering management dilemma. Thank you for joining us on the deep dive. We hope this look into professional requirement specification has given you plenty of depth to consider for your next systems architecture project.